Good morning. Today I'm going to talk about production function. The firm's production function for a particular good Q shows the maximum amount of the good that can be produced using alternative combination of capital K and labor L, where you have K is equal to F of KL, and that is what we know already. So in the cost lecture as well as the other lectures also follows the same. So let us go to the concept like marginal physical product. So it's a very simple concept to study variation in a single input. We define marginal physical product as the additional output that can be produced by employing one more unit of that input while holding other input constant. So marginal physical product of capital MPK, which is equal to a change in Q by change in K. This change is actually a partial change. Okay, so which is equal to F of K. So marginal physical product of labor, which is called FL, or MPL, which is equal to dou Q by dou L. So uh, the marginal physical product of an input depends on how much of that input is being used. So in general, we assume diminishing marginal productivity there, so which is actually nothing but the dou MPK by K, dou K, which is equal to the second order condition of F and K, which is always less than 0. So that is, it is negative. So if your marginal productivity of labor or capital falls, means the difference of the difference is going to be negative. So this is applies in every context. So because of the diminishing marginal productivity, 19th century economist Thomas Malthus worried about effect of population growth on labor productivity. But changes in the marginal productivity of labor over time also depends on changes in other inputs such as capital. So we need to consider FLK, which is often greater than 0. So if together, if capital labor been applied, then there is always a possibility that the output is always a positive one. So that is what does it mean. So average physical product of labor productivity is often measured by average productivity, which is APL by output by labor. So which is noted as Q by L or FFKL by L. Note that APL also depends on amount of capital employed. So in a two input production function case, this is going to be even easier because we were been discussing this is from the very beginning of this micro lectures. Suppose production function for a firm can be represented as Q is equal to F of KL, which is equal to 6000 K square L square minus K cube L cube. So if that is the case, to construct MPL and APL, we must assume a value of K. Let K 10. The production function then becomes Q is equal to 60,000 L square minus 1000 L cube. So this is what is actually there. There are many examples of the similar kind of different textbooks you can apply also and work out. So in the book which we use is actually Walter Nicholson's. In that book also it is there, third edition or any edition you will see some of this lecture. Now the book is also available in, I guess, as an online version. So marginal productivity function is MPL, which is equal to dou Q by dou L, which is equal to, as I said, 1020 120,000 L minus 1000 L square, which diminishes as L increases. It implies that Q has a maximum value in it. So if you have 1,20,000 L minus 3000 L square, which is equal to 0, is actually max. So you have an L maximum which is 40 L, which is equal to L square. That means the L and L 40 is actually the case. So the labor input beyond L reduces the output. So this is what is the optimal output level. To find average productivity, we hold K and solve APL Q by L, which is 60,000 L minus 1000 L square, so your AP reaches at its maximum where dou AP L by dou L, which is equal to 60,000 and 2000 L, which is equal to 0. So what does it mean? It means it is actually 30. So in fact, when L is 30, both APL and MPL are equal to 90,000. Oh, sorry, 9 lakhs. So that's when APL is at its maximum, APL and MPL are equal in that context. So which is gives us to make a, isochrone map to illustrate the positive map is uh, an illustration of possible substitution one input for another. We use an isochrone maps, and isochrones shows those combination of k and l that can produce a given level of output q0. That is f of k l, which is equal to q0, is what is actually called an isochrone. So each isochrone represents the different level of output. Output rises as we move northeast. So that is from higher the slope of an isochrone shows the rate at which L can be substituted for K. So this is what is actually very important. Ka and La combination is there, as well as KBLB combination is there. So this slope is in fact gives the rate at which L and K being substituted. So marginal rate of technical substitution is what is called the slope in this context. So RTS is greater than 0 and is diminishing for increasing output for labor. So the marginal rate of technical substitution shows the rate at which labor can substitute for capital while holding output constant along an isochrone. So RTSL for K, which is equal to inverse of d by k dk by dl, where q is equal to q0. So take the total differentiation of the total production function, then you will get this thing, that is dq is equal to dou f by dou l times dl plus dou f by dou k times dk, which is equal to the marginal productive labor times dl plus marginal productive capital, marginal productivity capital times. So along an isochrones, dq is equal to 0. So your MPL times DL is equal to MPK times DK, which is in that sense, given all the other things here, then you the constant, the rate of technical substitution L for K is equal to the inverse of dk by dl. Or what you say, if it is if we drop all this in negative signs, you will get MPL by MPK, which is an inverse relation. Because of MPL and MP will both non-negative, RTs will be positive or C. So however, it is generally not possible to derive a diminishing RTS from the assumption of diminishing margin productivity. So this is a very important point. Just to show that isochrones are convex, we would like to show that RTS, that is this total change of RTS with respect to labor, is going to be less than 0. So since RTS is equal to FL by FK, then the DRTS by DL is equal to DFL by FK divided by DL. So then you will get this thing, and using the fact that the dk by dl, which is uh, inverse or fl by fk along an isochron, and Young's theorem of fk, which is equal to flk, which is what is gives in this context. So but we're not actually concentrating too much on this, therefore I am So now let me come to the diminishing RTS case. Suppose the production function is this thing. The numbers are actually this. You can substitute with anything, and you can find out a different answer. So don't worry much about all these things. So a production function of marginal productivity of labor with respect to FL with respect to this quantity, let us derive this thing. So these marginal productivity will be positive for values K and L for which KL is less than 400. So because FLL is equal to 12,000 1200 K square minus 6K cube L, and FKK is actually 1200 L square minus L 6KL cube. Okay, so this production function exhibits diminishing productivity for sufficiently large values of K and L. So yeah, thus for the production function RTS is diminishing through a range of K and L where marginal productivities are positive. For a higher value of K and L, the diminishing marginal productivities are sufficient to overcome the influence of a negative value for FKL to ensure convexity of the isochrone. So this is very very important aspect which everyone has to keep in mind. So how does output now respond to the increase in all input together? So this is what this comes under the returns to scale case. Suppose that all input are double, would double the output is a question. So returns to scale have been of interest to economists since the days of Adam Smith, where Smith identifies two forces that come into operation as input are doubled. One is greater division of labor and the second one is specialization function. So loss, then this comes very important, that is greater division of labor with the specialization function and loss in efficiency because management may become more difficult when the larger scale. This is our diseconomy, is what is many people call diseconomy, um, because of difficulty in managing the firm size. So if the production function is given by Q, which is f of KL, and all inputs are multiplied by the same positive constant, that is T is greater than 0, then you have the following effects of output with respect to returns to scale. So then you have a constant return, decreasing return, and an increasing return case. So uh, that means the result is going to be greater, or lesser or constant. So it is possible for a production function to exhibit constant return to scale for some level of input usage and increase or decrease returns for other. So economist refers to this degree of return to scale with the implicit notion that only a fairly narrow range of variation in input usage and the related level of output is being considered. So constant return to scale of production functions are homogeneous of degree 1 in input, that is FTK, TL is equal to T1, FKL is equal to DQ. So this implies that the marginal productivity functions are homogeneous of degree 0. Okay, if a function is homogeneous of degree k, its derivatives are homogeneous of degree k minus 1. So this is what is actually the case which we have to keep in mind. So the marginal productivity of any input depend on ratio of capital labor, not on the absolute level of these inputs, and the RTS between K and L depends only on the ratio of K to L, not the scale of operation. So the production function will be therefore homothetic. Geometrically, all of the isochrones are radial expansion of one another. So this is what is actually the case. So along the ray from the origin, constant K by L and R returns to scale can be generalized to production function with an input. So if that is the case, you have this following. So if the input are multiplied by positive constant, we have the equations. Okay, and in that case you have a constant, a decreasing and increasing return. So it is also important to keep as part of the return to scale case. So elasticity substitution, the elasticity substitution sigma measures the proportionate change of k by L relation or relative to proportionate change in RTs along with. So this is nothing but the responsiveness of responsiveness towards substitution. Okay. Yeah. Both RTS, this is actually called the responsiveness for A. RTS K by L will change as we move from point A to B. So if you change along with, then the elasticity responsiveness also will change. So both have a different theta in that sense. So if sigma is high, RTS will not change much relative to K. The isocone will be relatively flat. And if sigma is low, the RTS will change by a substantial amount of K by L changes. The isocone will be sharply curved. It is possible for sigma to change alone an isocone or as the scale of production changes. So generalizing the elasticity of substitution to many input case raises several complications. So if we define the elasticity of substitution between two input to be the proportionate change in the ratio of the two input to the proportionate change of in RTS, we need to hold output and level of other. Now, in the case of linear production function, suppose that the production function Q is equal to f of KL, which is equal to AK plus BL. This production function exhibits constant return to scale. So that is, then it will definitely looks like FTK TL, which is equal to ATK plus BTL, which is equal to TAK plus BL, which is equal to TLKL. Also isocones are straight lines, so RTS is also constant. So you will get a sigma which is equal to, so this is what is actually your case. So where your sigma is infinite, that is you have a perfect elastic case. So in the fixed proportion case also you have the similar things. Capital labor must also be used fixed ratio. So the firm will always operate along a ray where K by L is constant. Because K by L is constant, sigma is equal to 0. So what you get is the reverse of an earlier one. No substitution between the labor and capital is possible. So you will get the points in which the intersection of these two cases. That means there is no substitution between. So for simplicity, we will place it as nail shape. So K is actually fixed between B by A, where your sigma is equal to 0. Now in the Cobb-Douglas case, this is not the case. So Cobb-Douglas, this production function can exhibit a return to scale in the following. A plus B is equal to 1, constant returns to scale, and A plus B is greater than 1, increasing returns to, and it is less than 1, then it is decreasing returns to scale. So Cobb-Douglas production function is a linear in logarithm. Therefore, ln Q is equal to ln A plus alpha ln K plus beta ln L. So A is the elasticity of output with respect to K, B is elasticity of output with respect to L. If you move towards the CS production function, then suppose that production function you have a Q which is f of KL, where K rho plus L rho times gamma by rho, which is where your rho is less than or equal to 1. It can be any number, or rho can be non-zero, where you have gamma which is greater than 0. So if gamma is greater than 0, then increasing return to scale is the case, and the gamma is less than 1, then it is decreasing. For this production function, sigma is equal to 1 by 1 minus rho. So that is the rho is equal to 1 is simple linear production functions, and rho minus 1 is infinite fixed proportion production function, and the rho minus that is inverse rho is equal to 0 is a Cobb-Douglas case, which we have said. Now, generalized limit case we have already seen, and that is it is sigma is there, the sigma is 0, therefore there is no substitution. So, technical progress case of production where your method of production changes over time following the development of superior production technique, the same level of output can be produced with a fewer input. The isochron therefore shifts in. Suppose that the production function is Q, which is equal to AT FKL, where AT represent all influences that go into determining Q other than K plus K and L. Changes in A over time represent technical progress. A is shown as a function of T, and change in A by change in T is of course positive. So if that is the case, then differentiating the production function with respect to time, we get this thing, that is change in Q by T, change in T which is equal to change in A by change in T, that is dA by dt times f of KL plus alpha, A times df KL by dt. Now we can derive the same, expand the thing, divide by Q gives us the following, that is dQ by dt by Q, which is equal to dA by dt by A plus dou f by dou K by f of KL times dk by dt plus etc. So in this case only two commodities. So then dou f of L dou f by dou L by f of KL times dL by dt. So you can keep expanding in that sense, and finally for any variable x, dx by dt by x is the proportional growth rate in x, denotes that gx, or denote this by gx, then we can write the equation in terms of growth rate. So you may be having gq which is equal to ga plus all the equations we discussed earlier. Since dou f by dou k times k by f of k L, which is equal to dou q by dou k times k by q, which is actually e qk. Okay. Now again for the other things also you will get, for the labor you will get. So in a nutshell, you can sum up it with the GQ, which is equal to GA plus EQK, GK plus EQL, GL. So this is what is actually the two things which you get. Now you incorporate technical progress also inside. So this can be expressed with the help of Cobb-Douglas case. Then with the logarithm case also we can be extended. So the important point which I would like to make as the following, like if all but one of the input are held constant, the relationship between the single variable input and output can be derived. The marginal physical productivity is the change in output resulting from a 1 unit increase in the use of the input assumed. Then the entire production function can be illustrated by an isochron map. The slope of an isochron is the marginal rate of technical substitution. It shows how one input can be substituted for another while holding output constant. Again, isochrones are usually assumed to be convex. They obey the assumption of the diminishing RTS. Then this assumption cannot be derived exclusively from the assumption of diminishing marginal productivity. One must be concerned with the effect of change in one input on the marginal productivity of other inputs. And the returns to scale exhibit by a production function record how output respond to proportionate increase in all input. If output increases proportionately with input use, there are constant return to scale. The elasticity of substitutions sigma provides a measure of how easy it is to substitute one input for another in production. A high sigma implies nearly straight isotherms, a low technical progress shifts the entire production function and isotherm map into a new direction, and technical improvement may rise from the use of more productive input or better